So to begin with, we can start with the definition. We define what is an analog signal as it pertains or as it is defined under the PLCs. An analog signal is a signal with an amplitude that varies continuously with the time. And here it means that time is continuous, yeah, and within a given amplitude range. You know what is an amplitude as far as the time graphs are concerned. That is, amplitude is the maximum displacement. So the maximum displacement of an analog signal, that is what we are calling an amplitude, and how it varies continuously with the time, that is an analog signal. So in other words, we are saying that an analog signal is defined for every instant of time within a given interval, and a signal can be continuous in time but not in amplitude, and therefore, strictly speaking, not an analog signal, but we usually call it an analog signal anyway. Both discrete and analog signals can be represented as a unique function of frequencies that are called signals frequency spectrum. This is then a description of the frequency content of the signal. We have the filtering process that entails when you're trying to convert those signals. And this process, that is the filtering process, is the process where the frequency spectrum is modified or converted, or you can say manipulated to satisfy a given or desired specification. That is the filtering process. We're going to later on discuss this in detail. You said the filtering process is a process where the frequency spectrum is modified or converted or manipulated to satisfy some set specifications. And this can involve amplification. You know what is amplification? That is multiplying the signal quantity, or suppression of a particular frequency range, or you can say removal or isolation of a particular frequency component. Use of these filters are many, but usually the goal is to reduce the signal contamination. That is, when we say signal contamination, as far as PLCs are concerned, it means reducing the noise that comes around with the signal, and the noise that has been added during transmission of a signal, or the disturbances that are the result of inaccuracies in measurements. So first of all, we're going to deal with the digitalization of analog signal. That is like converting this analog signal into digital signals that can be accepted by the PLC system. So digitalization of analog signals. Digitalization of the analog signal. So most signals that are processed are analog to begin with. They are analog by nature because, like when you're taking temperature, that is an analog signal. But you take it through a number of processes, including the filtering that you have said, to convert it to a digital signal that can be accepted by the PLC. This one we discussed when we were doing the digital signals. But the power and flexibility of computers and microprocessors, and also the PLC and other digital equipment, have made it easy and vital to digitalize analog signals and process the digital signals in various ways. And we're going to see how a typical signal processing system how that process goes about. You're going to see the stages or a block diagram to represent this. When you're doing this digitalization of analog signals, the first operation, that is the input filtering, it reduces measurement noise and limits the frequency content of the signal for digitalization. And then that is the first step or the first process. Then number two, the actual conversion of the analog signal to a discrete or digital signal then takes place. This is after the first process, that is the filtering. You say the filtering is the reducing or the doing away with the noise that comes around when you are taking measurement of this signal. So the first step when you are digitalizing an analog signal, you said is the input filtering, and you said this is reducing measurement noise and limiting the frequency content. Then step number two, or operation number two, you have said this is the actual conversion now of this analog signal to a discrete signal. And this is why you see the analog to digital converters being used. The actual conversion of the analog signal to a discrete signal. You said here we can involve analog converter. AD converter. After that, we have step number three, and this refers to what happens within now the digital equipment, that is the PLC or a PC for that matter. Analog signals can be read into PLC via the analog input modules or the input blocks, and such blocks come in many variants, but all have the inbuilt filters, which I'll say that the work of these filters is to limit the frequency content of this signal, and also to reduce or do away with the measurement noise. So I want to share with you that block diagram of these steps. I don't know if the others can see. Mr. Nguru, you're saying you can't hear my voice clearly. I don't know if the others can, because somebody had confirmed he's getting me clearly. It was Muredi. So that is the process, the typical operation that happens in a signal processing system. That is the digitalization of the analog system. So you've said the first step is the filtering, and this is the filtering of the input signal. And you said this is to reduce the noise and also limit the frequency. Then there is that the second process, that is the analog to digital conversion, whereby now these analog signals are converted to a discrete or digital signal. Then you have the third step. This one now happens now inside the PLC system. That is the calculation and the manipulation of that signal. And then we have now digital to analog converter, and then we have the output filter. You can draw that diagram in your notebook as as part of your short notes. So copy that block diagram in your notes, then we proceed. Okay, we can now proceed. So that is the first step, the filtering. We are going to make some short notes about the same, the filtering process. And here we can say that we have already seen what is filtering as far as signals and PLC or PC is concerned. And we have said this is the reducing of noise. All measurement signals will contain electrical noise, And this is the noise that typically appears in form of high frequency oscillations around the measurement signal itself. So when you talk of noise, we don't necessarily mean the noise, the audible noise. No, we mean noise as it relates to frequencies. And you said this noise is the noise that typically appears with the high as a high form or form of high frequency oscillations around the measurement signal itself. And such measurement noise is often the result of disturbances from other electronic equipments, for example, from the power supply or from operational equipment such as motors and pumps. And measurement noise can also be as a result of changes in the physical process of the physical process variable that is being measured. An example of this is measuring the level of fluid surface when the surface is disturbed. That is, it has ripples. That is like waves. So those ripples will be now the noise that will be filtered out when taking these measurements. And we can have some diagram representation of this. So you can see from the shared screen, the first graph represents measurement signal that contains noise. You can see that those discontinuous lines, those are the representation of a signal that has those noise. And you've said an example maybe is when the ripples in in fluid. So that is that measurement signal with noise, and you can see after it has been taken through the filtering, there is now the frequency response in this diagram here to first and second order low pass filters. So regardless of the cause, it is necessary to filter the signal in order to remove or reduce the noise. And if the measurement noise has a frequency content that corresponds to the natural changes or in measurement signal, and then we have to a major problem. Then it is not possible to for this process of filtering out or the removal of this noise and the reduction of the frequency. As mentioned, the energy of the noise is generally is in a higher range on the frequency scale than the energy in the signal. And in this way, the noise can be removed or reduced by use of a low pass filter. Uh, this is simply to a low pass filter works by allowing all energy that lies below a certain frequency, and that certain frequency it can be called a cutoff frequency. That all energy that are below that energy, that cutoff frequency, it is uh, it is allowed to pass the filter unhindered. When energy that is above that cutoff frequency is reduced in strength. So you set a cutoff frequency, and then all energy below that is allowed to pass, and all energy or all frequency above that cutoff frequency is reduced in its strength. And so by so doing, even when you plot a graph, you have a smooth linear graph as compared to the one that works with regard to filtering of frequency. You say that it works by allowing frequencies below cutoff frequency or a certain frequency, the cutoff frequency to pass, and those frequencies that are above that cutoff frequency, they are reduced in strength, and therefore the general output will be a harmonious frequency that is in harmony. The next thing that we can talk about is the analog to digital conversions. And this is achieved by using converters. I believe you have done this in digital electronics, converters, and they involve a number of steps. So the analog to digital converters they are used to digitalize these analog signals. And to avoid this, using the AD converters for each individual analog signal, normally you use a multiplexers that routes one signal at a time into this analog digital converter. And there will be an interface that contains a sample and hold circuit. This is under the multiplexers. Yeah. So these analog to digital conversions can also include several other steps, and you're going to see a figure to represent this. And these steps include the sampling at fixed time intervals, that is sampling of the period symbolized by T, and also the use of this one that you have said, the sample and hold circuit, and this is for quantifying and also coding. And then we will have the quantifying, and quantifying here, we mean that for each sample, it is rounded off to the nearest level possible. And then for the coding, each quantity value is converted to a binary code, where and when the samples are quantified and coded, then the signal is usually referred to as the digital signal. So if you're told to describe the analog to digital conversion, then you need to talk about these four steps: the sampling, the use of the sample and hold, the quantifying, where we say this is rounding off to the nearest level possible, and also the coding, which is now after you have quantified your values, then they are converted to a digital binary code. That those are the four major steps that are involved in analog to digital conversion: sampling, sample and hold, quantifying, that is the rounding off to the nearest level possible, and the coding, which is converting to a binary code. And therefore, the output, whatever you have now after this, it will be a digital signal that will be in form of a binary code. We can talk about these processes, like the sampling, and say that during sampling in the digital to analog conversion, from that shared screen, you can see the illustration of the sampling. There's that curve, that graph of the amplitude in the y scale, and then we have the variable time in the x-axis, and then you have the quantity being sampled there, and you can see the representation. So this is the sampling amplitude in the y scale and the time in the x-axis. Obviously, time this can be presented in seconds. So after you have sampled that, you can represent your signal here, and then now you convert this to a discrete signal by use of the binary coding. So from this figure, you can see the signal before the sampling, and also the signal after the sample and hold. And this is represented in that circuit. So for the next step, the sample and hold, I want to believe that you've roughly put that into your notebooks. That's why I'm trying to be a bit slow. So the next step is the sample and hold, and we said this function is to maintain the amplitude, to maintain that, to ensure that this amplitude that is being sampled is constant until the next sample is done or arrives. And this is done to permit the analog to digital converter process, and this process to complete the sampling. And this is both also to quantify and to code. And an illustration of this is what is being shown here in these two diagrams, the sample and hold. So after you have done the sampling and holding, the next step we said is to quantify. Quantify. So for quantification, we can say that now these digital systems, the PLCs, the microcontrollers, or maybe the PCs, they use a certain number of bits to represent and store a value. So this means that the discrete sampled values are rounded off to the nearest possible level, and we say that is the quantification, to round off to the nearest possible value. And how big this round off is, it depends on the number of bits that are used in the quantification, and more bits gives better resolution. So the more you round off to the nearest bit, the better the resolution will be. So that is the quantification. And then after that, now you convert, you use now the coding to convert now the signal that you have into a discrete or to a digital coded signal. So basically, that is all about the conversion of analog signal into a discrete or a digital signal. It involves the four steps that we talked about. Any question? Next, I want us to talk about the properties of these analog input modules. Properties of the analog input modules. Is of analog input modules. So for every PLC distributor, they can usually offer several different analog input modules that are completely that completely depend upon the requirements of the user. And if you're going to select the proper modules, there are often many aspects that somebody should take into consideration before the selection. So we're going to discuss some of this, some of the important aspects to consider before the selection of an analog input modules. Some of those considerations, they include one, the electrical measurement ranges, and also this can also be the physical ranges. What are the measurement ranges that your input modules should can accommodate? That is the first consideration, the electrical or physical measurement ranges. Two, the requirement for accuracy, and this one is, we'll say this one is achieved by looking at the resolutions. So there they are, the requirement for accuracy, that is involves the resolution. Three, the number of,
the number of,
and then the
and
requirement,
then the requirement.
for speed, and this includes the updating speed of that module, and also the how those signals, now the analog signals, are physically connected to the PLC module. That's another consideration. And the last one is the requirement for use in explosive environments. So this one depends upon the type of PLC that you want to use, and where you're going to use it, the environment of the PLC module, and the conditions that comes about. Other criteria that can be used to determine the selection of an analog input module include the tolerance, and this means that how much physical abuse, such as maybe dust, we talk about the interferences that protects the PLC with relation to its environment. So how much dust or temperature, etc., those kind of conditions will this input module tolerate, and how much will the individual inputs tolerate. That can be another criteria to, or a property to consider when selecting an analog input module. Another thing to consider is the linearity. When you talk of linearity, this means that is your module going to be linear across the entire range of measurement? That can also be a property to consider. Also, the calibration and adjustment. When we talk of calibration, we mean that can you add a bias the measurement to compensate, or maybe for a poorly installed sensor or a transmitter, so as to compensate for the voltage drop over long cabling holes. And the last criteria that can, or a property that you can consider, is the filtering possibilities. When you talk of filtering possibilities, this is we said filtering is how you can reduce the input, the measurement noise. How how possible is it? How your analog input module, how will it be able to achieve this, the filtering process? So those are some of the properties to consider. I want to believe that you have copied that. As we conclude the class, is that we're almost done with this topic. Next, we are going to be discussing the networking of these PLCs and the signal conditioning, and also their scan operation as far as the PLCs are concerned. So I don't know if anybody has a question up to that point before we can end the class. I'll update the notes for you for this topic. For those guys who are not able to take good notes, I'll give comprehensive.
You are now unmuted.
Yes, Gura, do you have a question or something?
You are now unmuted.
Oh, I don't have, though my phone has been having charges. Sijui ni nini, lakini nitaangalia. Imekuwa hanging.
Okay, no problem.
Okay, no problem. I'll share the notes. Okay,
Anybody
thank
with
you.
Anybody with the question?
if there is no question, then you can enjoy your afternoon. Those guys who are mathematics 3 will meet tomorrow. And yes, Simon, saying something is wrong with the system. I don't know what exactly you mean.